So in this lesson, I'm going to be talking about the process that's called electrolysis. Now, electrolysis is different from a voltaic cell simply because a voltaic cell the reaction occurs spontaneously without the need for outside energy. Electrolysis requires energy. So here are two diagrams right here which show you what happens in electrolysis. Notice it's almost identical to a voltaic cell, except you need some sort of voltage source for electrolysis to occur.
As I just mentioned, voltaic cells and electrolytic cells are very similar. Okay? In both a voltaic cell and an electrolytic cell, a redox reaction is occurring. So some substance is being reduced and some substance is being oxidized. Now, the reaction for a voltaic cell is spontaneous, as I noted, while it is not spontaneous in an electrolytic cell. Therefore, when we're talking about a voltaic cell, the cell potential will be positive and the Gibbs free energy will be negative, right? When the cell potential is positive and the Gibbs free energy is negative, that tells us that a reaction is spontaneous. While in an electrolytic cell, the cell potential is going to be negative and the Gibbs free energy will be positive. All right, so ultimately, as you guys saw in the previous lesson, one of the biggest struggles with a voltaic cell and with an electrolytic cell is figuring out what is being reduced and what is being oxidized. Now, while for an electrolytic cell, the reaction is not spontaneous, and for a voltaic cell it is, you're going to have the same process as far as figuring out what is being reduced and what is being oxidized. Specifically, for both a voltaic and an electrolytic cell, the way to determine what's being reduced and oxidized is you choose the half reactions that will give you the most positive cell potential possible. So even though we know that an electrolytic cell is going to have a negative cell potential, you still aim to get the most positive value possible, and ultimately it will end up being negative, but you try and make it as positive as possible, right? Flipping whichever reaction has the most negative reduction potential to make it be oxidized, so that when you add the oxidation half and the reduction cell potentials, you end up with as positive of a value as possible. And we will look at that in just a second when we talk about electrolytic cells. But let me go a little bit more into detail now about electrolytic cells themselves. I just wanted to note all of this for you guys to realize that voltaic cells and electrolytic cells, you can treat them identically, not only with how exactly the cell runs, but also in determining what's being reduced and oxidized. The only difference is that an electrolytic cell does require some power source, and we'll look at how that influences our work in a minute, but let's get into electrolytic cells.
Well, the question is, if there's only that difference, why do we really care? Well, it brings up a couple of concepts that we need to talk about. The first one is a qualitative one. If you've ever bought a piece of jewelry, in all likelihood, it's been coated with a metal. And so electrolysis is how that piece of jewelry was coated. What happens, as you can see on the right-hand side, if you start with a nickel anode, right, nickel solid, and then you have a ring that's just made out of whatever metal, what you can do is actually have that nickel become nickel ions by oxidizing it. And then if you run a power source through that, what that can do is actually cause the nickel ions to then be reduced and actually cause solid nickel to coat a piece of jewelry. And so that's what they do. It's called electroplating. That's what they do in order to coat your jewelry. So the reason why for a voltaic cell, why you need two different elements is because in a voltaic cell, that happens spontaneously, so you need different cell potentials. But if you're going to provide the energy, you can actually take a solid and put it onto another object by first making it into an ion and then reducing it so it goes from being an ion in solution back to being a solid. So there's actually some math that's incorporated with it. The first concept that's new is Faraday's constant. And what Faraday's constant is, it simply tells you that there are 96,485 coulombs of charge per mole of electron. And so we're going to be using that in just 1 second. The other piece of information you need to know is about amps. Now an amp is a measure of current, and that simply is 1 coulomb, which is a unit of charge, per second. So we can use those two pieces of information to answer this question right here. What it says is it asks you to calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps? Well, the first thing I need to do is figure out the reaction that's occurring, what exactly is going on. Well, if I start with molten aluminum chloride, that means I have aluminum ion. So I've got Al3+, okay? And that's going to produce solid aluminum. Now, the other piece of information you need to know, because this is a reduction reaction, meaning I am gaining electrons, then I'm going to have 3 electrons on my reactant side. So that's key when we use Faraday's constant in just 1 second. So I'm going to start off with my given, which is 10 amps. Well, 10 amps is the same thing as saying 10 coulombs per second. And so what I can do is actually solve first for the number of coulombs, the charge that's involved with 10 amps. So I can do that because the electrolysis takes 1 hour, which is the same thing as 3,600 seconds. And so I'm now in coulombs because my seconds canceled. And what I can actually do is I can get into moles of electrons by putting the Faraday's constant of coulombs on bottom and 1 mole of electrons up top. The next thing that I need to do, though, is I need to get into moles of just aluminum because I want to know how much aluminum I'm producing. Well, the reason why I wrote that reduction reaction above is because I know that 1 mole of aluminum is going to be produced for every 3 moles of electrons. And so I can use that conversion factor right there, put 3 moles of electrons on bottom, 1 mole of aluminum up top. And then I can get into grams by simply using my molar mass. And so when I do all of that out, I end up finding that I'm going to produce a total of 3.36 grams of aluminum solid by this electrolysis reaction.
All right, so I'm going to give you another example problem here. It tells me that the half reaction for the formation of magnesium metal upon electrolysis of molten MgCl2 is the following. Okay, so that shows the reduction half reaction for magnesium. It says calculate the mass of magnesium formed when you have a current of 60 amps over a period of 4.00 times 10 to the third seconds. So I'm going to start with my 4,000 seconds. Okay, and I'm going to be using my 60 amps as a conversion factor. So I ultimately want to get into grams of magnesium, so I'm going to first put seconds on bottom to get rid of them and coulombs up top. Okay, remember an amp is a coulomb per second, so I'm going to put 60 in front of coulombs and 1 in front of seconds. Now I'm in coulombs, but I want to get into grams of magnesium. In order to get into grams of magnesium, though, I need to get into moles of electrons. So I'm going to put coulombs on bottom, moles of electrons up top. For this conversion here, this is going to be Faraday's constant. Remember, Faraday's constant is 96,485 coulombs for every 1 mole of electron. So I'm going to 1 mole of electron, 96,485 there. I'm now in moles of electrons. So I'm going to put moles of electrons on bottom, moles of magnesium up top. If you look at that half reaction up there, I know that for every 1 mole of magnesium, I'm going to have 2 moles of electrons. And finally, now that I'm in moles of electrons, I can now get into grams of magnesium. So I'm going to put moles of magnesium up on bottom, grams of magnesium up top. I need to put the molar mass of magnesium, which is 24.30, and 1. And so when I multiply and do all the division, I get 30.2 for my final answer. All right? So we're going to look at an electrolysis reaction, and you guys are going to have to be able to anticipate what reaction is going to occur. So make sure that you pay attention to my explanation because this is the lab that you're going to do next block. And a lot of people struggle with this, so make sure you're clear. Rewatch this section if you need to. All right, so there are situations where a power source is needed in an electrolysis reaction. In these cases, the cell potential is going to be negative because it's not spontaneous or it's not thermodynamically favorable. But the reaction that occurs is going to be one that is the least negative, has the least negative cell potential. So in order to determine the cell potential of the electrolysis reaction for nickel chloride, what you're going to do is you're going to first consider all your possible reactants. So if nickel chloride has been dissolved into water, your reactants are going to be nickel ions, chloride ions, or water. So remember, nickel ions, chloride ions, or water have to be your reactants. So let's first look at nickel. So nickel 2+, for it to be a reactant, you're going to have the reduction reaction of nickel, which you can see on your table, which is just that. Okay, not too crazy. Okay. And the cell potential for that is the negative 0.28 volts, because that's just as written. For chloride, though, if you notice on the table, you don't have chloride as a reactant, you have Cl2. because it's Cl2 plus 2 electrons. So what you need to do is you need to flip that reaction. It's the third reaction on your reduction half reactions. So I'm going to flip that and write 2Cl minus produces Cl2 plus 2 electrons. This is what messes most people up. Chloride is one of your reactants, so it has to be a reactant. You can't put Cl2 as your reactant. So I'm going to take the reduction potential, which is positive 1.36, and I'm going to flip that and make it negative. So for water as a reactant, you have two possible reactions. So if you look through all of these reduction half reactions, there's one where water is automatically a reaction. It's the fourth from the bottom. Or if you look, and if you're looking at your table, the fifth from the top, water is a product, you could flip that reaction. So you have two different possible reactions. So for the one from the fifth from the top, I just need to flip that reaction. So it becomes 2H2O produces O2 plus 4 H pluses and 4 electrons. So I just need to take that positive 1.23, which is the reduction potential, and just make it negative. And then the last option is for the fourth from the bottom, the 2H2O plus 2 electrons, okay, because water is a reactant there, and the cell potential is the negative 0.83 volts. So the hardest thing for this right now is remembering nickel ions, chloride ions, and water have to be your reactants. For the nickel, you're given that reduction reaction, so you're good. For the chloride, you have to flip the reaction that's given, because the reaction that's given is a reduction, while the chloride ion being a reactant, that would be an oxidation reaction. And then the same thing for water. One reaction is a reduction, the one on bottom, the one on top is oxidation. Now what I need to do, as it noted, your cell potential is going to be negative when you add them up, but you want the one that's the least negative. So remember, my reduction reactions, my two possible reduction reactions are the nickel ion and the very bottom water one, because those are where the electrons are being added, while the two middle reactions, those are my oxidation reactions. So what I'm going to do is I'm going to compare my reduction reactions, so the top and the very bottom, and my oxidation reactions, and whichever ones are least negative, that's the one that's going to happen. So if I compare my nickel and my water, the top one and the bottom one, since the nickel is less negative, right, that one is going to be the one that occurs. Okay, so that is the reduction reaction that occurs. For the chloride versus the water, since water is less negative, that's the one that's going to occur. Okay, now, so the nickel is my reduction reaction, the water is my oxidation reaction. Okay, now I just need to balance these and add them together. So I've got to multiply the nickel by 2 and then add my reactions together, and that is my redox reaction that I get. Then I'm going to just add together the cell potentials. So I have the negative 0.28 from nickel, and I have the negative 1.23 from the water. And so what you end up getting for your final answer is negative 1.51. So just as a quick review, first figure out what your reactants will be. So nickel ions, chloride ions, water. Then make sure those are your reactants. So for the nickel, it is a reduction reaction. Chloride, it's oxidation. Then for the water, you're going to write the oxidation half and the reduction half reactions, those two that exist, and then you're going to figure out which one it should be. So whichever oxidation reaction is least negative, whichever reduction half reaction is less negative, add them together, and then you'll get your final voltage. So now that we've actually calculated the cell potential for this electrolytic cell, what would we as experimenters actually observe? So you've got nickel ions reacting with water. What's being formed? Because you wouldn't actually see this reaction, but you could see what is being formed. So we've got O2 forming, so you would see bubbles. You've got H plus forming, so that would be forming an acid. Keep in mind, if it's H plus, you're forming an acid. If you're forming OH minus, you'd be forming a base. And then you've also got solid nickel forming as well. So you could be asked a question like that with respect to, okay, how would you know that reaction, how could you confirm that reaction actually occurred? You'd see bubbles in this case, your pH would be less than 7, it'd be acidic, and you'd have a solid nickel forming. All right, so as I had noted in the previous practice problem, for some reason, this concept is what students always mess up on. So I really want to make sure that we're clear on how exactly to write these reactions, and then you're going to also practice them in the lab itself. Okay, so here I've got copper iodide. Keep in mind, I need to figure out what my 3 possible reactants are going to be. So since I've got copper iodide being dissolved in water, my 3 possible reactants will be Cu2+, I-, and H2O. Those are the only things that can exist as reactants. So I'm going to start off with my reduction reactions. Okay, so I have two possible reduction reactions. If you look at this table, you'll notice I've got Cu2 plus 2 electrons producing copper solid. So that is going to be one option for a reduction reaction. The cell potential is 0.34 volts. The other option is with water. So if you search the table, below it has water reacting with 2 electrons to produce H2 and 2 OH minus. The cell potential is negative 0.83 volts. Notice, as I had said before, copper 2 plus and water are two of my three possible reactants. So you can't flip this around at all. Those have to serve as reactants. All right, let's look at your oxidation options. So if I look at my table, notice that I've got I2 plus 2 electrons produces 2I minus. I cannot put I2 plus 2 electrons as a reduction reaction because I2 is not one of my possible reactants. 2I minus is. So I'm going to flip that reaction. So I'm going to have 2I minus produces I2 plus 2 electrons, and instead of a positive 0.54 volts, which is the reduction potential for I2, I need to flip it so it's going to be negative 0.54 volts. And then if I look, water could also be a reactant that is being oxidized. So if you search your table, fourth from the top, you'll see you have O2 plus 4H plus 4 electrons gives you 2 waters. Keep in mind, you've got to flip that guy because water has to be the reactant. O2 and H plus cannot be. So I need to flip that reaction. That gives me this. The original cell potential was positive 1.23. Now it's negative 1.23 volts. Okay, so if we look at this then, I got to figure out what's being reduced and what's being oxidized. And as I had noted in the previous example and what I said at the beginning of this video, remember, regardless of if it's a voltaic cell or an electrolytic cell, I still want the cell potential that will make the overall cell potential the most positive possible. So for reduction, notice the Cu2 plus has a cell potential of 0.34 volts. So I'm going to get rid of the water option because that's more negative. And then I'm going to choose the iodine because that's less negative. And then I'm going to add them together. Notice I'm going to have Cu2 plus 2I minus when I'm combining these reactions together to form copper and iodine. Okay, I add the cell potentials and I get a cell potential of negative 0.20 volts. So how would I know that this reaction occurred? How would I confirm it like we will in the lab? Well, look at your products. Your products are copper atoms and iodine. Copper atoms will show up as pieces, flecks of copper. You'll see solid copper forming, okay, because it's not an ion, it's now a solid. And then I2, keep in mind that I2 is actually a solid at room temperature. So you'll actually see solid iodine forming as well. So you'll see solid copper and solid iodine forming.